Hey guys, Mr. Smith here, and shooting a video lesson on increasing and decreasing functions. It's our first lesson of our second unit on curve sketching and optimization. And you guys really actually know quite a bit about when a function's increasing, decreasing. We're just going to formalize a few things today and play around with this idea a little bit. Should be pretty good. So maybe before calculus, you would have said that an increasing function is one that kind of moves like a line that has a positive slope or a negative slope if it was decreasing. But we have a new way of talking about increasing or decreasing functions in terms of the derivative. A function is increasing simply if the derivative is greater than 0, which means it's the tangent line at those values is greater than 0. So ways a function can look like that, an increasing function. So there's that's like a linear function that's increasing. Or you could have like a quadratic function, a part of a quadratic function, or an exponential function increasing, like so. But you can also have a function like the log function from your grade 12 functions course that is kind of leveling off over time, but still increasing. Still, as you're moving to the right, the graph is moving up and up and up. All of those rough sketches there, the tangent line would be positive for any of those. Those are all increasing functions. And then conversely, a decreasing function has a derivative that's less than 0. And then we can just kind of mirror those drawings there. I'll draw a linear function, rough sketch, that's decreasing. Maybe a decreasing exponential function, or like a left-hand side of a parabola that opens upwards. And then I can also draw something similar to what I had before with the log one, maybe something that looks a bit like that. Just some different visuals of decreasing functions. All those three at the bottom would be decreasing. They're kind of moving down as you move to the right. Their tangent lines would be negative. The slope of the tangent lines would be negative. So let's look at an example here. So we have a cubic polynomial, and we now have the skills to actually concretely say, when is this function increasing or decreasing? So right away, you guys should be able to see that because the leading coefficient is positive, it's an odd degree polynomial, that the end behavior is going to be from quadrant 3 to quadrant 1. Our cubic polynomial could look something like that, or maybe it doesn't have any turning points. Maybe it could look like that. So it could be increasing, then decreasing, then increasing, or it could be always increasing. We don't really know too much until we start looking at the derivative. So let's dive in. This isn't exactly a terribly difficult derivative. So what we're going to do is we're going to find the derivative first. And then we'll look at when that derivative is increasing, decreasing, or sorry, when the derivative is positive or negative. That will help us tell if the function is increasing or decreasing. So it's a quick derivative, 6x squared plus 6x minus 36. And so the derivative there, prime x, 6x squared plus 6x plus 36, or minus 36. What we're interested in, if we want to find out when is this positive, when is it negative, we're going to set it equal to 0 and find those points where it's equal to 0. And then we'll be able to look at those as kind of like dividing lines and look in between those regions and see what the sign of the derivative is. I'm just going to tuck over a equals 0 over here. Let's solve this quadratic equation. So this one has been cooked up, so it's pretty easy to solve. We can factor this. Divide out the 6, and then x squared plus 6x minus 6. And then we can use simple trinomial factoring. What adds to 1 multiplies to minus 6, x plus 3, and x minus 2. So the two values that make this derivative equal to 0 are x equals minus 3 and x equals 2. So we really have to look at regions less than -3, between -3 and 2, and more than 2. I'm going to set it up this way. So this is similar to what you did in grade 12 functions, where you like solved a polynomial inequality. So we have 5 regions we're going to look at. So we're going to have when x is less than -3. We'll just have a column here for when x equals -3. For when x is between -3 and 2, talk about when x equals 2, and then we'll look at what happens when x is greater than 2. All right, so let's continue. So we're just going to pick some values for the derivative that are like pick a value that's less than -3, and we'll see if the function's increasing or decreasing on that interval. So I'll pick, let's say, pick x equals -4. We can plug -4 into our derivative. So you guys can take a second to do that if you'd like. You can pause the video anytime to do this stuff as well. We'll see if I can use mental math here. This might be a bad idea. 96 minus 24, it is a bad idea. I'm going to actually just get my calculator. All right, got my calculator here. So when I plug in -4 into the derivative, 6 times 16 minus 24 minus 36 equals 36. So if you plug in -4 into the derivative, you get 36. And since that's positive, we know that the graph is going to be increasing. And we kind of already knew that from what we reasoned out the end behavior to be. When x is equal to -3, so I'm not going to use a test value. We're just looking at what happens when x equals -3. But at -3, the derivative is equal to 0. Yeah, it's one of the two values that made the derivative 0. And that means the slope of the tangent line is 0. What does the graph look like there? Well, it would be a horizontal line. Let's pick a simple test value in this interval, like x equals 0. When you plug 0 into the derivative, you get 0 plus 0 minus 36, which is negative. The graph will be decreasing. At x equals 2, we already found out the derivative is 0. Tangent line will be horizontal. Face out of there. And then finally, let's pick maybe a simple value, x equals 3, to plug in for this interval. F prime at 3 is equal to, so that's 6 times 9 is 54, minus 18, minus 36. X is greater than 2. What did I get? 6 times 3. Why did I get? All right, we're good. I'm just shooting this video after I put my kids to bed, so I'm not thinking clearly. 6 times 9 plus 6 times 3 is 18. Minus 36. I got 36, which means the graph is increasing. So you can kind of see the shape of the graph from looking at the signs of the derivative in these intervals. It looks like it's going to be kind of like this scenario here. And I'm going to just type out a little conclusion here. And then I'm going to head to Desmos and just verify that this graph actually looks like we thought it did. So I'll get some text here. We can say that the function is increasing when x is less than -3. It's also increasing when x is greater than 2, and decreasing when x is between -3 and 2. So we can concisely say when the graph is increasing, decreasing. It kind of fits what we know about cubic polynomials and their end behavior. And then I have the graph pulled up here. I just made it ahead of time. And this is a great idea for you guys to do as well. If you're doing questions like this, just to have it graphed ahead of time, and then you can just keep comparing and see if your work checks out. So this is the function, and you can see that it has a little maximum point here at -386. So the graph is increasing all the way to x equals -3, and then decreasing all the way to this minimum point, which is at 2 minus 39. and then increasing again all the way to infinity. So everything kind of fits together. So nothing crazy new. It's increasing, decreasing functions. We're just going to do some exercises here, thinking about the derivative and what it means in terms of the original function, in terms of increasing, decreasing. Let's dive in, and you can feel free to pause the video at any time here and just try these on your own. But let's look at this function. So this function in blue, we have the graph of the derivative of some function. And it's actually easy to tell what the derivative is. This is just a horizontal line at -2. This question is saying that the derivative, f prime of x, is equal to -2. Now, we don't exactly know for sure what the original function is, but we know that it looks something like this. The original function must be -2x. It could be -2x, but it could be -2x plus 5 or -2x plus 10. We don't exactly know, but the derivative is going to give us 0. So you can think of it, if it helps you, you can think of the original function being -2x. I'm going to graph that here. Something like so. And I'm just going to freestyle my straight line. Good enough for the time of day it is. But let's actually think about this question in terms of increase and decreasing. The derivative, look at it. It's constantly -2. The derivative is always negative. That means the original function is always decreasing. Is the line y equals -2x always decreasing? Yes, it is. And its slope is always -2. So everything fits together. In the second example, we have a derivative function that's linear. So the original function might be quadratic. Well, it is quadratic. And because the derivative is positive when x is less than 2, that means that the graph will be increasing when x is less than 2, and the graph will be decreasing when x is more than 2. Why? Because the derivative is positive to the left of 2 and negative to the right of 2. So what would that look like in terms of a parabola? I'm not going to actually dive into what the equation would look like, but what does a quadratic function look like that's increasing and then decreasing? Well, it could look something like this, where we have some vertex and a parabola that opens downwards, where it's increasing, reaches the maximum, and then decreasing on the other side. -2 is that kind of dividing line, where the slope of the tangent line at 2 would be 0. It's increasing to the left and decreasing to the right. Again, thinking about the sign of the derivative, positive or negative, that tells you whether the graph is increasing or decreasing. Let's do another exercise here. So these next two kind of relate more to the one we did in this original. The derivative of both of these two functions are quadratic. We can see a graph of the derivative here. They're both parabolas, meaning the original function is going to be a cubic function. But will they both look something like the one we saw earlier? So I'm going to let you guys have a think on that. Think about whether the graph is increasing or decreasing, and when it turns from increasing to decreasing. If you want to pause the video and try to reason that out, you can. So I would encourage that. So I've given you that chance, and I'm going to keep moving forward now. So if we look at this derivative, this derivative is positive to the left of 1, so it's increasing. The derivative is 0 at x equals 1, and then the derivative is positive again to the right of 1. It's increasing as well. This function is always increasing, except at one point, x equals 1, where it's momentarily equal to 0. What would that look like as a cubic function? Well, I'm just going to draw something like it could look like this. It could look like your standard cubic y equals x cubed, just kind of shifted a little bit. Could look something like that. That's a function that's always increasing, except the derivative is momentarily 0 because the tangent line is horizontal at x is equal to 1. Otherwise, it's increasing. And you can see it matches the derivative very well. However, with this next one, we can see that x equals 1, and x equals 3 are two spots where the derivative will be 0. The derivative is negative to the left of -1, so it's going to be decreasing. The derivative is positive between 1 and 3, increasing, and then the derivative is negative, so our function will be decreasing. Again, this is the graph of the derivative, and we're giving a possible graph of what the original function looks like. So what would a cubic function look like that's decreasing, then increasing, then decreasing? It would kind of look like the flip-flop of what we did earlier. So try not to make my space too gummed up here, but something like so, decreasing to increasing to decreasing. That's the idea. Let's look at an application here. So we have a function that models the temperature of a person with a certain strain of flu. So we can see right away it's quadratic, and that this quadratic function will open downwards. So their temperature, just like a lot of people when they get sick, their temperature might start to spike up because they have a fever, and then when their fever breaks, it'll come back down. And we're going to look at the time interval for when the person's temperature is going to be increasing, where their temperature keeps getting higher and higher. Maybe as a parent, these are the kind of times where you're kind of worried, because after a certain point, you have to take your kid to the hospital. So let's have a look here. So don't worry about all the fractions and stuff. We're in calculus, so we can handle it. Let's start. If we're looking for when this is increasing or decreasing, we now have a tool to do that. That's the derivative. So let's find the derivative. So we'll bring down the 2. That's negative 10 over 18 times just d. And then the derivative of 15 over 9d is just 15 over 9. The derivative of 37 is 0. And that's our derivative. So it makes sense. The derivative is a linear function since the original was quadratic. And then as before, we're going to find out when is that equal to 0. A lot of ways we can do this. I'm actually just going to simplify 10 over 18 to negative 5 over 9 plus 15 over 9 equals 0. Time travel back to grade 9. You can clear the fractions out here by multiplying everything by 9. And you get minus 5d plus 15 equals to 0. And then we're basically done. I'm going to show a lot of my steps here. Minus 5d equals minus 15. So d equals exactly 3. So what we've seen is that at d equals 3, the derivative is equal to 0, which means the shape of the graph, horizontal tangent line. So d equals 3 corresponds to where our vertex is of this original quadratic function. And then what happens when d is less than 3? Is it increasing or decreasing? I know you guys know it's a parabola that opens down. It's going to be increasing. But we're doing these exercises so you can apply these ideas when we look at exponential, trigonometric functions, or even combinations of functions. So it's good exercise to do. Let's pick an easy one. I'm going to pick 0 here. I know technically it says that we're between 0 and 6, but that's okay. If you want to pick 1 or 2 or something, I'm tired and I just want to get this lesson done. So we're going to just pick 0. At 0, the derivative is positive 15 over 9, which means the graph is increasing. And then I'll pick a value to the right. I'll just pick, that's the region when d is greater than 3. We'll pick a value like 4. And the derivative, when d is equal to 4, so we have minus 5 times 4 is minus 20. Minus 20 plus 15 gives us minus 5 over 9. And that is a negative value, so the derivative is negative. The slope of the function is negative. It is decreasing. And so if we want to conclude this question, when is the person's temperature increasing? So when is this temperature function increasing? It's when the derivative is positive, and that happens when d is less than 3. So the person's temperature is increasing from 0 to 3. And that's when their temperature reaches its maximum and then starts decreasing again. And FYI, tomorrow's lesson, we'll start to look at finding those local maximum and minimum values. We actually know what happens at d equals 3. But again, that's something for our next lesson. Okay, so let's do a couple more exercises. So in this question, we have some conditions to be met, and we're going to graph a possible function that satisfies these conditions. So what I'd like you to do is, in a second, pause the video, and you're going to think on what does this information that we're given actually tell us? Can you decipher the code? So don't worry about the graph yet. Pause the video for a second and think about what does all this information actually mean? And I'll unpause, and then you should unpause when you've done that. So I'm going to keep going. So hopefully you've taken a chance to do that. So sketch a possible function where f prime of x is greater than 0 when x is less than 0. So what does this mean? This means that it's increasing when x is less than 0. What does this next part mean? F prime of x is less than 0 when x is greater than 0. That means it's decreasing when x is greater than 0. And what does this last bit mean? F at 0 equals 4. Well, that's just telling you there's a point. The point there, this graph goes through the point 0, 4. So what is a possible graph that's increasing to that point 0, 4 and then decreasing after that? Well, I'm going to give you guys a second to maybe give that a go. There's many different possible graphs that work. I'll give you a couple. All right, so hopefully you've given that a try. I'd say the easiest kind of graph would be just like some kind of parabola. That I might do a better job of that. That's opens downwards, so it's increasing to the point 0, 4 and then decreasing afterwards. But there's actually many types. Some of you guys are taking data management, and you're going to work with functions that look like this. This is called a normal distribution or a bell curve. We have the same maximum as 0, 4, but it levels off to a horizontal asymptote of y equals 0. But this function as well is increasing all the way to 0, 4 and then decreasing all the way after. But I think if you came up with that quadratic function that opens downwards, that's great. That's totally good enough. I just wanted to show you that there are other possible functions that would work. Okay, and I think the last thing we'll do, one more exercise like that. So it's the same thing again. Maybe pause the video and look at the information given and think, what is this information actually telling us? So I'll let you guys do that. Hopefully you've given that a go. And I'm just going to keep moving here. So f prime of x is greater than 0 when x is less than -1. So this is telling us a region of increasing. It's increasing when x is less than -1. And when x is greater than 2. So it's increasing on this interval as well. And maybe I'm going to just put some dashed lines here just to keep everything separate and organized. F prime x is less than 0 when -1 is less than x is less than 2. It's decreasing between these two values. And then finally, f at 0 equals 0. That's just telling us that the y value in x equals 0 is 0. Okay, so we need to draw a function that's increasing to -1, and then decreasing from -1 to 2, and then increasing again. So it doesn't matter where we put we know that it's going to be increasing, decreasing, increasing. I'm going to put maybe a local maximum here and a minimum here. They can be higher or lower as you like. It just has to be higher than 0, 0. So we have something that looks like this. And then decreasing, that's just terrible. Let's try that again. Increasing reaches that maximum. I can't draw. And decreasing, that's fine. Decreasing, that's going to do. We're just going to call that good enough. So something like that. Increasing when x is less than 1, -1, and greater than 2, passes through 0, 0, and decreasing in between. And that wraps up the lesson. So hopefully you're convinced, like, we didn't do anything crazy new today, except connect increasing and decreasing to the derivative. And we did a bunch of exercises, getting you guys used to thinking about derivative being positive, increasing, derivative being negative, decreasing, and of course, derivative being 0, meaning horizontal tangent line. So we'll use these ideas more in our next lesson when we look at finding maximums and minimums of functions as well. Hope you guys enjoyed the lesson. Please reach out if you have any questions. Take care, guys, and we'll see you soon.